Hello, we would like to describe the operation of TAMI software, which is Tel Aviv Molecule Identifier. So we will present here three files for your review. The first one is the Agilent generated eval demo file, which you can see here at the upper left, and it is included in any GCMS, so it is also in your GCMS if you have an Agilent GCMS. We will zoom over the first peak. As you can see here, we will make an average on the baseline of this peak, and we'll get this way the mass spectrum. We do the averaging on the base of the peak in order to reduce as much as possible mass spectral skew and increase the ion statistics. Now we will send it to NIST library search as usual by double right click, and you can see that NIST library identified it as dodecane with identification probability of 40.8% and high matching factors of a little bit above 950. Here on top you have the TAMI software. You can see the window, and we are not going to go over all the details. TAMI software begin by confirmation or rejection of the NIST library identification. How does it do this? It is working only on the basis of the molecular ions, which you can see here, meaning it ignores all the fragmentation pattern and takes into consideration only M, M+1, and M+2. So TAMI begins with downloading from ChemStation itself the experimental data of M, which is normalized to 100%, then M+1, M+2, and M+3. Here we limit our consideration only to the molecular ion and three isotopomers. Now, NIST library, as you can see here, generate a list of 100 candidates for identification, and the first one is dodecane, so dodecane is the most abundant. So what we do, we take from NIST all the 100 elemental formula, and we find out that there are 63 different elemental formula, and we generate, via the computer software, we generate the isotope abundances of all these 63 elemental formula. Then we compare it with this experimental data, and we generate a matching factor. The matching factor is written here, IAA match, which is isotope abundance analysis match, which is 902 out of 1000. You have here the average error, and you can see that NIST identification is confirmed. The compound is the first in both hit lists. Note also that the identification probability was almost doubled from about 41% to about 80%. So we confirmed, what if we don't have this compound in the NIST library and we do not want to relate to the NIST library, which is, as you can see, is automated without any clicks. So the next level will be to make analyze. We do analyze. Now we don't have names. The first elemental formula is C11, H10, N2. Since we know the NIST identification and we trust it, you know that this is incorrect. Second one is the correct elemental formula, C12, H26. Now we further improve the TAMI generation of elemental formula by using the mass accuracy. We know that the mass is not only 170, as is written here, but it is around 170.3. So we click here, and we use the mass accuracy filter within plus minus 0.14 AMU. Even though this is a unit resolution quadrupole mass analyzer, we generally trust the 0.3 to be accurate within plus minus 0.14 Dalton. So now we will do the analysis, and we get the correct elemental formula, C12, H26, and you can see here the combinatorial. The computer generated 102,000 elemental formula. It operated chemical valence consideration, and as a result 325 possible chemically correct molecules were found. 3 passed the mass accuracy filter, and 1 of them passed the minimum match restriction, which is seen here as 800. So you've seen that TAMI is working, and what you've seen also is that it is simple to operate, and in addition it works with centroid files. So this is the industry standard. Let's go and take another example. I will average here at 10%, and you can see here that the molecular ion is likely to be 154, even though there are M-1, M-2, etc. Double right click, and we get here biphenyl, and the identification of biphenyl is confirmed. And as you can see here, NIST identification confirmed, and we will do analyze as before. Note that the TAMI software identified correctly the molecular ion as 154. Analyze. Now we don't have the name biphenyl because this is analyzed to give you a table of elemental formula. Number 1 in the table of elemental formula that includes 4 compounds, as you can see here, is C12H10, which is the correct elemental formula. Okay, we've done something simple. Let's go now to another more advanced file. I will load the file, and I will go to a standard test mixture that we use here at Tel Aviv University for our students' lab. You have here 1, 2, 3, 4, 5, 6, 7 compounds, plus we added at the end PFTBA for improved mass accuracy. Now we are working in the profile mode, and I will make here average of the PFTBA, and you can see here the mass spectrum of PFTBA with standard DI, and we'll send it to NIST identification, and NIST identify it as perfluoro-3-butylamine. TAMI has here in the tuning has mass tune function, and the mass tune function, as you can see now, there is no mass tune function, but we'll click here, one click, PFTBA, and now you have here a correction function based on the difference between the known calibration mass and the measured mass. The known masses are based on the fact that we know what are all the fragment ions of PFTBA, and the measured mass is what we measured. And now you have to realize that we are measuring with 4 decimal places. So I will use it, and I will show you why can't we use it, because we have here a profile. Let me show you what I mean by profile. I take this peak, average it as usual, and you can see that it is profile. When we are working with profile, the Agilent generates mass bar every 10th of an AMU. So you can see that peak is at 194.1, but there are other peaks. And what we can do is now a kind of weighted average, meaning give here the height times the mass, plus the height here times the mass, plus here, etc., divided by the number of mass bars that we are including in it. I'll do NIST lab research, which is caffeine, and for caffeine we are getting 194.0995. Note that the mass accuracy here is 101 ppm, but we can click here mass tune and use the mass tune function that we used before, and now we are getting 0.5 ppm. Admittedly, this is too good to be standard. We are typically below or at about 40 ppm, but sometimes 40 ppm average mass accuracy can give us 0.5, half a ppm mass accuracy. Now, as you can see here, green light means that we confirmed the NIST identification, and now we can click here, ppm, and what is important is not that this is half a ppm, but by which mass window do we trust it completely to be accurate. And we trust it to be accurate within 100 ppm. So the maximum mass error is 100 ppm. So now let's do analyze. Remember, C8H10N4O2 is the correct one. C8H10N4O2 is number 1 out of a table of 4. And we can do another compound here, just to show that this is general. We get here anthracene, and if we'll do the analyze now with the mass tune, with the mass accuracy filter of 100, note that the mass error is 25 ppm, and we get a table of only 1 compound. I'll get to a more difficult identification. This is the last peak. NIST library says chlorpromazine, and TAMI says that NIST library is confirmed. We have here a mass error of 74 ppm with a matching factor of 991. So let's do the analysis. And it's C17, H19, N2 chlor-sulfur, which is the correct elemental formula of chlorpromazine. Note that the computer generated 182,000 elemental formulas, and after including chemical valence consideration, this number went down to almost 3,000, 2,896, and 187 of them passed the mass accuracy filter. And the table here includes 37 elemental formula within the constraints of 800 for isotope abundance analysis, yet the correct elemental formula is number 1, which is a good achievement. Now you ask me, as you've seen, I always show that NIST library was correct because these are non-compounds. So let's go to another compound which is not in the NIST library. This is a synthetic compound. It was done with GSMS with cold DI, but that doesn't matter. This is a synthetic organic compound, which almost by definition is not included in the NIST library. So I'll send it to the NIST library. And well, the NIST library is 20.6%, so it's poor. And we get here gray light, which means that the molecular ion of the first library hit is missing. And this is an indication that this compound is not included in the NIST library. Also, identification probability is very low and close to number 2. So we'll go to analyze. Before going to analyze, we need, since this is centroid data, we need to go to Dalton and include here 0.14 and eliminate the mass tune because we did not do any mass tune. And now we'll do analyze. And we get green line. Green light means that number 1 is far away from number 2, etc. So we can trust it. And indeed, C14, H18, N2, O3, S2 is the correct elemental formula, as later on was confirmed by NMR and via the synthetic route of this compound. So in summary, TAMI provides the sample elemental formula from single quadrupole GCMS data files, similarly to costly high-resolution mass accuracy MS. In fact, it can do that at a level of 1 ppm mass accuracy alone. In addition, TAMI improves the mass accuracy of the quadrupoles. And very importantly, TAMI automatically links with the NIST library for its automated identification, confirmation, or rejection. TAMI works also with standard centroid files. Data collections and analysis is performed with the known instrument data analysis software, and TAMI is compatible with the Agilent ChemStation and MassHunter, Thermo, Excalibur, and Chromeleon, and the Advion's LCMS Data Express. As a result, TAMI is also very easy to use relatively. TAMI is also dongle-free, and thus it can be available for a free trial period. Thank you very much.